Hello class, and welcome to section 8.4, which is about modeling with quadratic functions. By the end of today's lesson, you will be able to apply what you have used about quadratic functions to model some real-world situations. The first thing we're going to look at is an area model. We use this with rectangles in order to calculate different areas and be able to adjust these rectangles quickly. So, finding the area model for the rectangle, then we're going to graph the function. Then we're going to calculate the potential x values to plug into this function. So starting with modeling the rectangle, this is going to take us back to chapter 7, part 1, where we need to use our FOIL method to multiply the two binomials that they give us. So we know in order to find the area of a rectangle, it's going to be base times height. So our base and our height. So first we're going to start with x times 4x, which is going to give us 4x squared. Then we're going to go to the outside, x times 8, so plus 8x. Then the inside, 3 times 4x, plus 12x. And then last, 3 times 8, so plus 24. Then we can go ahead and simplify this to get our final area model, which is going to be 4x squared plus 20x plus 24. So that is our area model for this rectangle. Then we're going to go ahead and do the graphing part. In order to do that, you need to be able to find the vertex, the axis of symmetry, and the y-intercept. So we're going to start with that y-intercept, which is going to be 0, 24. Then we're going to find our AOS, which takes the opposite of b. So we've got x is equal to negative 20 divided by 2 times our a value, which is 4. So we're at negative 20 over 8, giving us an AOS value of x is equal to negative 2.5. Then in order to find our vertex, we're going to go ahead and plug that back into the equation. So I've got 4 times negative 2.5 squared plus 20 times negative 2.5 plus 24. When you plug that into the calculator, you're going to get an answer of negative 1. So your vertex point then is at negative 2.5, negative 1. So if we go ahead and put that on the graph, we're going to go over negative 2.5 and down 1. So that's your vertex point, which means you can also draw in that axis of symmetry at negative 2.5. Then we're going to graph our y-intercept. Now, notice we need to go up to 24. So what we actually need to do is renumber this graph, which is something we can do easily. So I'm going to have to fix my vertex because I have to count by the same amount for both the positives and the negatives. I need to get up to 24. So I'm going to go ahead and count by 4s. 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. And it would be counting by the same in the opposite direction, so we'd be going negatives of those numbers. So now when I fix that vertex, negative 2.5, negative 1, is going to be much closer to that y-intercept. And then I'm going to graph my y-intercept at 0, 24 and mirror my point 2.5 over. So I get this nice curve right here. So now that we have our graph, our next and final piece that we have to do is figure out our potential x values. To do this, we actually go back to our original side values. And we know that in order to have a rectangle, the value of the side has to be greater than 0. So we're going to look at both sides, and we're going to say the x plus 3 has to be greater than 0, and the 4x plus 8 has to be greater than 0. Now, we have an inequality here which we can solve. So for the first one, we're going to subtract 3 from both sides, and I get x is greater than negative 3. For this next one, I'm going to subtract 8 on both sides. I've got 4x is greater than negative 8, dividing by 4, and I get x is greater than negative 2. Now, we need this statement to work for both sides. So when you're trying to decide which inequality is your actual answer, you want to look for the bigger value that you get. So in this case, we're looking at negative 3 and negative 2. So that means this inequality right here, x is equal to negative 2, is your potential x values. So you can plug in anything above negative 2, and that is going to give you a solution to this graph. I want you to go ahead and try this one on your own. First, I want you to find the quadratic function. So for your quadratic function, you're going to get x squared plus 6x plus 5. Now I want you to go ahead and find the axis of symmetry, your vertex, and your y-intercept, and then put that information on the graph. So for your axis of symmetry, you've got negative 3, which puts the vertex at negative 3, negative 4, and your y-intercept is at 0, 5. Last thing I want you to do is find the inequality for the potential x values. We set each of our original sides greater than 0, then we get our answers. Negative 1 is greater than negative 5, so our potential x values are x is greater than negative 1. We can also use this for an application, so for plugging in to solve. So a company offers a rectangular pool, sizes based on the dimensions shown. Each pool includes a deck around it with a 4 feet width, so you can see that right there. First, we want to find the quadratic function that is going to model the entire space for the pool and the deck. So when we're looking at this, again, we need our base times our height. If we look at the base, we have this 2x, but then we also have this extension of 4 feet on both sides. So that means our base is 2x plus 8. Same thing happens with the height. We start with our x, but we have the extension of 4 feet on either side. So we've got x plus 8. Go ahead and finish solving to find the quadratic function on your own. So for our model, we have 2x squared plus 24x plus 64. Then it asks a follow-up question, which says, if Caroline wants a 15-foot wide pool, how many square feet of her yard will be used? So what that means is you are going to need to plug 15 in for your x values. So we put 15 in the spot of our x's, and I want you to go ahead and in your calculator, calculate the value of space that will be taken up. When you plug this in, you're going to get a final answer of 874 square feet of space being utilized. The other type of model that we're going to be looking at with quadratics is called a vertical motion model. So this is looking at when objects are moving, how quickly are they moving. These are going to use our inverted parabola, so a downward facing parabola. And this 16 in the front comes from the speed or the motion of objects due to gravity. So you don't really need to know the exact reasoning behind this negative 16, but just know that this is a factor of gravity that is accounted for in these equations. So our height, h of t, at time t, can be modeled by negative 16t squared plus the initial velocity. So we call that v0 times the time. So v0 is going to be replaced with a number. That's going to be initially how fast the object is traveling. Plus h0, which is going to be the initial height that your object starts at. So, for example, we have a diver who jumps from a 30-foot platform with an initial velocity of 16 feet per second. So you can see that as a diver comes off of a platform, it forms a very narrow, but still a quadratic parabola. So in order to complete our model here, again, our equation was h of t is equal to negative 16 t squared plus our initial velocity times time plus our initial height. So they give us the information based in the sentences. So I'm going to say h of t is equal to negative 16t squared plus my initial velocity, which is 16 feet per second, so 16t, plus the initial height. So the platform where the diver started was 30 feet tall. So this is our quadratic model for the diver's path. Then it also asks us to figure out the diver's maximum height. So we're looking at this peak right up at the top, and that is going to, again, be our vertex. So it's going to go back to solving for our vertex. In order to solve for the vertex, the first thing we need is the axis of symmetry. So I'm going to take x equals negative b, so negative 16, over 2 times my a value, which is also negative 16. Negative 16 divided by negative 32 gives me an x value of 0.5. Then you're going to go ahead and plug that back into your equation. So negative 16 times 0.5 squared plus 16 times 0.5 plus 30. And when you plug that whole thing into the calculator, you get an answer of 34. So what that means, what your final answer would be for this problem, is the diver's maximum height. So the diver's max height is 34 feet after 0.5 seconds. So you want to make sure you include your labels in the final answer. In this case, it was 34 feet maximum and the height of 0.5. So now we are looking at another vertical motion problem with a basketball shot. LeBron shoots a jump shot with an initial velocity of 18 feet per second and an initial height of 6 feet off of the court. First thing I want you to do is write a function using the vertical motion model. So your function should be h of t is equal to negative 16t squared plus 18t plus 6. Now I want you to go ahead and find the maximum height of his shot. So for our maximum height, we plug in our negative b over 2 times a and get 0.5625. Then we take that exact value and plug it into our function. And the maximum height is about 11 feet after about a half a second. If it asks for specifics, then you would obviously say 11.0625 feet after 0.5625 seconds. But for the most part, it is okay to round on these problems. If you have questions about this or anything else from the lesson, please let me know when you get to class.